Today in the Physics Funhouse, we are exploring simple harmonic motion. The two examples of simple harmonic motion that we study in Physics 1 are the simple pendulum and a mass on a spring. We're going to focus today mainly on the mass on a spring because it's a little bit simpler to understand. There's no changing angles or anything like that. The definition of simple harmonic motion is simply periodic motion, as in motion that repeats regularly over a time interval, hence the harmonic in simple harmonic motion. Periodic motion that has a restoring force, meaning a force that pulls the object towards an equilibrium position, which is proportional to displacement. So focusing just for a second on our mass on a spring example, we remember from way back at the beginning of the year that when you hang a mass from a spring, it stretches the spring out, and the more force you put on that spring, the more it's going to stretch out. And so when I put this mass on the spring and then gently lower it, it reaches an equilibrium position where the force of gravity and the force the spring exerts are balanced. When I displace this from its equilibrium position, now it's going to move in simple harmonic motion because the net force on this thing as it moves is always towards equilibrium. So let's take a few minutes to draw some pictures to see if we can understand what that means before we move on to describing the motion of something moving in simple harmonic motion. Okay, so let's investigate the forces on our mass on a spring system. Obviously, anything that is in the Earth's gravitational field is going to have a gravitational force, and that gravitational force doesn't change. And so when it's just hanging there, it's got some gravitational force Fg. If I were to displace it above its equilibrium position, it would still have the same gravitational force, Fg. So over here, same size gravitational force. And the same is going to be true when I pull it down and displace it below its equilibrium position. It's going to have the same gravitational force. And so it's important to understand that that is still true. The force of gravity is not changing. The other force involved, however, is the spring, and the spring force does change with the stretch of the spring. So right now, because the mass is in equilibrium, the spring force must be equal to the gravitational force, just up instead of down. And so I'm going to draw a spring force here that is basically the same size as the gravitational force. When I displace this thing upwards, with the spring stretched less than it was stretched before, the spring force is going to be smaller. Remember that the force exerted by a spring is proportional to its stretch. And so at this point up here in its motion, the spring is not stretched as much, so the force is going to be smaller. It would still be there, because the spring is still stretched a little bit, but not as big as it was before. Likewise, when it's below its equilibrium position and the spring is stretched a lot, then the force is going to be very large. So over here, a large spring force. And so if we investigate all those free body diagrams, here those two forces will be balanced, just like it is right now. And so we could say that the net force is 0. When the object is above its equilibrium position, the gravitational force downward is bigger than the upward spring force. And so the net force would be directed downward. And over here, when it's below its equilibrium position, the upward spring force is larger, and so the net force is up when it's below equilibrium. So what we notice is that the net force is always towards the equilibrium position. When it's above equilibrium, the force is down. When it's below equilibrium, the force is up. And so the restoring force is always towards equilibrium. And because the force exerted by the spring is proportional to its stretch, as we displace more from equilibrium, the force is going to be larger. And so the net force is going to increase with increased displacement from equilibrium. And you can see that if you just kind of move it down a little bit and let it go, it moves up a little bit. If you move it down farther and let it go, Okay, so here we have our mass on a spring, and I've got a motion sensor sitting underneath there, and that is connected to the capstone program. And we're going to record the position of our simple harmonic oscillator as it moves with respect to time. So this is positions over here, and this is times down here. So let's get it moving. Pull it down, 3, 2, 1, release. And let's go ahead and record the data. Okay, so you'll notice that the maximum displacement, let's go ahead and auto scale this, maximum displacement of just more than 0.10 or 10 centimeters is equal to the negative displacement of just more than negative 10 centimeters, and that it's got this sinusoidal shape like this when it was at its maximum vertical position. That would be this point right here, equilibrium there, and then its maximum downward position, negative amplitude right there. Okay, so here in the capstone program, we've got our video over here, and it's synced up to the data collection, and I've selected position versus time over here, and then I've gone ahead and marked the equilibrium position of our mass on a spring on the video frame here. So what I'm going to do is I'm just going to click through frame by frame. Right now we'll notice that it's below equilibrium, and we have a negative position over here. Now it's moving upwards. And at this point right here, the center basically reaches that equilibrium position. So you notice that this is right on 0. And then click forward a little bit more, and now it's reached its maximum upward displacement amplitude. And so you'll notice here it's above equilibrium. And so I'm going to try to play this back at 1/8 speed. Let's try 1/4. And just to let it play for a second. So you'll notice that when it crosses 0, that's when it's at its equilibrium position. When it goes down, there it is at its maximum downward displacement. And then there it goes back to its maximum upwards displacement. So we get this sinusoidal curve. It curves up and down, looks like a sine wave. And we'll get into the mathematics of sine waves or curves in our next video. So the position time graph is relatively easy to understand because it literally matches what you see. Like equilibrium is 0 position, we get 0 on the graph. The next thing we're going to look at is the velocity, and the velocity does not match up with the positions. And from this graph, you can start to see that if you kind of pay attention to how close together the dots are. Remember that the change in position with respect to time is the velocity. So up here, those dots are close together, the position isn't changing very quickly, but as we go towards equilibrium, those dots are getting more spread out. So next, let's look at the velocity versus time and see what that looks like. Next, let's talk about the velocity of a simple harmonic oscillator. So let's go ahead and displace this thing to its positive amplitude and then release it. What you'll notice is that when it reaches its amplitude, it's got to go from moving up to down, or vice versa, moving down to up, right up here. These 2 points, the amplitude, is where the velocity is 0. Before it goes from up to down, it's got to stop in between. And so our starting point is just to recognize at the maximums, at the amplitude, the velocity of a simple harmonic oscillator is going to be 0. And so if I kind of reset this thing real quick, if I displace it down, because that's probably the easiest thing to understand, as I release this thing and it starts to travel upward, it's going to accelerate upward. Because displaced below equilibrium, it's got a net force going up. And so as it rises, it's going to speed up until it reaches this equilibrium position. After it reaches that point and it continues to go up, it starts to slow down, because now the net force is downward instead of upwards. And so the skinny of all that is that the maximum velocity gets reached at the equilibrium position. And it's going to be changing directions each time it passes through. And so if I release it from down here, as it travels through equilibrium, the maximum velocity is upward, stops, reaches its maximum velocity again, but this time going downward. And so the maximum speed is just at its equilibrium position. And so kind of matching this drawing with that, this position right here represents it moving upwards towards a positive amplitude. And so I'm going to draw an upward arrow, call that Vmax. It stops when it reaches its amplitude and then starts to go downward, reaching a maximum velocity again, but this time downward when it returns to equilibrium. And then when it reaches its lowest point again, it reaches a velocity of 0. So if we kind of think about what a graph of this will look like with respect to time, here we have a big maximum velocity. So if I make this a velocity versus time axis, it's going to start at some maximum velocity, go to 0, go to some maximum but negative velocity, and then back to 0 again. So this graph, just like our position graph, is sinusoidal, kind of sort of like that. But notice that it's lagging, if you will, the position. Position of 0, velocity is at a maximum. Velocity is 0, the position is at a maximum. Position is at 0, velocity is a maximum again, and it keeps oscillating like that. And so the velocity time graph is a sinusoidal graph as well, but it's going to be shifted one way or the other from the position time graph. And so we can investigate the velocity graph a little more carefully with a motion sensor and compare it to a position time graph. Let's grab our motion sensor again and check that out. Okay, so I've got my object moving in simple harmonic motion still, and this time I've got the capstone program set to give me velocity versus time data. So I'm going to go ahead and collect the data in real time and try to sync these side by side so that you can see the thing moving as the data is being collected, and then we'll take a more close examination of the data and compare it to the position versus time data. So let's just hit record on this and observe the velocity versus time. So you'll notice that same sinusoidal shape, kind of looks like a wave oscillating back and forth. Notice that the largest negative value of just greater than 0.3 is equal to the maximum positive value of just greater than 0.3, which should make sense. It should have the same energy at equilibrium regardless of which direction it's moving, so it should have the same speed at equilibrium regardless of which direction it's moving. Okay, so we still have our video of our object moving up and down, and this time I've got the velocity versus time selected. And the first little bit is being real laggy for some reason, so I've gone ahead and advanced the video up to this point right here, where it's reached its maximum positive velocity. And so positive velocity would be moving upwards, and here will be moving upwards fast. If you'll notice over here in the video frame, the mass is at equilibrium at this point. And so I'm going to click through this thing frame by frame so we can see it clearly. Right now it's moving fast upwards. And as it moves up, it starts to slow down. And it reaches a velocity of 0. So here it is at 0 velocity when it reaches its maximum vertical height. And so now it's essentially stopped. If we click forward, now it's moving down and speeding up. You'll notice the dots getting further apart, and it reaches its maximum downward speed again when it reaches the equilibrium position. So here it's moving downward fast at equilibrium. It moves past equilibrium, so it's still moving downward, but now it's slowing down, and slows down and eventually reaches a velocity of 0 again. So that's when it's at its lowest point There it is at equilibrium, and it's moving downward. And I can tell it's moving down without actually seeing the video because the velocity is negative. And so as I click forwards, I should expect it to keep moving down. Reaches a velocity of 0 as it reaches its bottommost point. Now it's going up, reaches a maximum upward velocity, so a big positive number here. Keeps moving upwards. Lost the video again. And that's where it stops. My laptop just doesn't have enough memory to run the screen capture and capstone with the video at the same time. And so what we need to kind of be able to do is interpret this graph of velocity versus time for something moving in simple harmonic motion, and basically just be able to relate it to the position. And so at this position right here, the position being equilibrium, it's got its highest up and down speed, and then when it reaches a position of way down low, so at its maximum displacement, that's when it's got its velocity of 0. So the displacement and the velocity are basically opposites of each other. When the displacement is 0, the velocity is really big. When the displacement is at a maximum, that's when the velocity is 0. Next, we're going to look at the acceleration versus time graph and see if we can interpret that. Okay, so looking at the acceleration versus time graph, I still have the data synced up with the video, and I've gone ahead and advanced this until the acceleration is essentially 0. And what you'll notice over here is that the object is at equilibrium, which should make sense. At equilibrium, the forces are balanced, so the upward spring force and the downward gravitational force are balancing each other, and so we would expect 0 acceleration. It moves forward because it's already moving forward. And so don't confuse 0 acceleration with 0 velocity. This is actually when it's moving its fastest, and so if it's moving up, it will continue to move up. If it's moving down, it will continue to move down. And then the acceleration will start to be not 0. So kind of advancing this forward, what you'll notice is that my accelerations are becoming negative and the positions are becoming positive. So notice that it's up here above equilibrium and the acceleration is negative. So why is that? Remember that the definition of simple harmonic motion is that the restoring force is towards equilibrium. So with the spring not stretched very much, the spring force now is smaller than the gravitational force. So the net force on this thing is directed downward, and so we get a downward net force and thus a downward acceleration. If I keep clicking forward, returns to equilibrium again, so forces are balanced, no acceleration. And it continues to move downward, and now the net force is positive. And so when it reaches its lowest point, I get the biggest upward force. And so that's because now the spring force is larger than the gravitational force, giving me an upward net force. So playing it back at 1/8 speed, equilibrium, maximum, so big negative acceleration, equilibrium, negative max, so big positive acceleration, equilibrium, upward max, big negative acceleration, so on and so forth. And so remember that it's always accelerating towards equilibrium because the net force is always directed towards equilibrium. And so the positions and the accelerations are always going to have opposite signs. That's kind of an important thing to remember about something moving in simple harmonic motion. They'll always be in opposite directions. When it's displaced below equilibrium, the acceleration is upward, like right now. When it's above equilibrium, the acceleration is always downward. Okay, so here I've got all three quantities graphed right on top of each other. So the top graph is position versus time, the middle graph is velocity versus time, and the bottom graph is acceleration versus time. And what you'll notice is that they sync up, but they don't really sync up. And looking at 3 seconds is kind of the best point because that's where it nicely lines up with one of these big vertical lines. At 3 seconds, my position graph is at a maximum. So that's when it reaches its highest point in its vertical motion. If we kind of just trace down here, notice that the velocity at 3 seconds is 0. And so when it reaches its highest point, it comes to a rest. And then down here, the acceleration graph is at its lowest maximum point. So that's when it's got its largest acceleration, but downward instead of upwards. And so at its highest point, it stops, and its acceleration is going to be very large, directed downward. If we look at a point where it crosses equilibrium, like right here, we kind of just trace downward, you'll notice that it's got a downward slope, and so it's moving downward at this point, a large downward velocity, and then the acceleration is 0. So when it's at 0 position, it's got 0 acceleration again, because that's when the forces are balanced. But that's when it's moving the fastest. So these graphs are all out of sync with each other. Like, they don't ever line up perfectly, but the maximum position, 0 velocity, largest negative acceleration. And so if we can remember that at equilibrium it's moving fast and has no acceleration, and that at its maximum displacement, its amplitude, it comes to rest and has its largest acceleration, and that the acceleration and position always have opposite signs, then that's what we need to know in order to be able to interpret and line these things up and determine what's going on. So let's recap what we've learned today and perhaps even draw a simple diagram that encompasses everything we've discussed so far. And so for our simple harmonic oscillator, here's its equilibrium position. We're going to call that x equals 0. When it is at its equilibrium position, the forces on it are balanced, and so it's not going to be accelerating at that instant in time, but it is going to have its maximum velocity, because that's after it's spent the most time accelerating up until that point. And so in the picture that I've drawn, where I'm going from equilibrium to a positive maximum, that would be the positive velocity's maximum at that position. When I reach the maximum displacement, that's when the object stops, because before it moves from up to down, it's got to stop in between. We call that maximum displacement its amplitude, and so this will be a positive amplitude. And then the net force is towards equilibrium. And so when it's at its positive maxima, that's when the net force is directed downward, and that means the acceleration is directed downward as well. And so at this exact moment, it's stopped, and then it's going to start to speed up, going downward due to that large downward net force. When it returns to equilibrium, the forces again are going to be balanced, but it's spent a lot of time speeding up, so it's moving downward very fast. When it reaches its maximum negative displacement or negative amplitude, the force is still towards equilibrium, and so you're going to have a large upward acceleration at that moment. So from 0, speeding up, moving up, it's going to reach its positive maximum velocity again when it returns to equilibrium. And so the graph of position and velocity and acceleration are all sinusoidal, but none of them are going to match each other. So the position and acceleration are both maximum when you are at the maximum displacement, but they're in opposite directions, so they have opposite signs. So next video, we're going to investigate the mathematics behind those curves a little bit more carefully and see what the difference between a sine graph, cosine graph, and negative cosine graph are, so that we can more generally understand the mathematics behind all this. Till then, ta-ta.